All right, we've been looking at tests for parallelograms, and now we're going to move to testing whether a quadrilateral is a parallelogram when it appears on the coordinate plane. Now, if we go back and think back over what our conditions are to prove that a quadrilateral is a parallelogram, well, we've got one that says that if both pairs of opposite sides are parallel. Now, when we're looking at something on the coordinate plane, one of the ways that we can determine that is we can use the slope formula, because parallel lines would have the same slope. And so just as a refresher, our slope formula is m equals y2 minus y1 over x2 minus x1. And if we find that both pair of the opposite sides of a quadrilateral are parallel, then we are indeed dealing with a parallelogram. Now, a second test is if both pair of opposite sides are congruent. In other words, do they have the same measure? And so when we're on a coordinate plane, then we have the distance formula. And the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. The square root of that is the distance formula. So here's slope, here's the distance formula. All right. Now, another way, but we're not going to determine that on a coordinate plane, is whether both pairs of opposite angles are congruent. But one we can solve, actually two more we can solve, is that the diagonals bisect each other. And what we would need to determine there is that the midpoint is the same coordinate. And so then we could use our midpoint formula, which is x2, I'm having a hard time making a 2 here, x2 plus x1 over 2, comma, y2 plus y1 over 2, comma. And in looking at the diagonals, the endpoints of the diagonals, and plugging it into the midpoint formula, if it has the same coordinate, then they do in fact bisect each other. In other words, both sides, well, it's at the midpoint, so from the midpoint between the segments, they are congruent. Now, a third way combines both the slope formula and the distance formula, where we just take one pair, we can just use one pair of opposite sides that we can prove to be both parallel and congruent. So in these exercises that we're going to do here in this little section, and this ties to example 4, which is on page 416 of your textbook, we have here's the two examples we're going to work on, where we're given the coordinates of the vertices. We plot those on the coordinate plane, and sometimes we're going to be asked to prove it using the distance formula, which is what we're going to do in the first one. Other times we're going to see the midpoint formula, and then sometimes we'll see both the distance and the slope, or maybe just the slope by itself. But we're applying any one of these three formulas, slope, distance, and midpoint, or midpoint, to in fact determine whether a quadrilateral is a parallelogram. Now we're going to work on a couple of these, so hold on. All right, so this is for the first set of vertices that we saw, where A, and I'm going to write those on here, where A is 3, 3, and B is 8, 2. And if you look closely on the graph, you can see that's where those are. C is 6, -1. And D is 1, 0. And in this set, we were asked to prove that this quadrilateral is a parallelogram by using the distance formula. So what we want to prove then is that this segment and this segment are parallel. No, excuse me, have the same distance. We're using distance formula. And so AB is congruent with CD, and that AD is congruent with BC. So let's work on AB first. So AB is going to equal the square root of, and I'm going to use the B as the 2 coordinates, 8 minus 3 squared plus, and then using the y coordinates, the 2 and the 3 here, is 2 minus 3 squared, square root of that. Okay, so the 8 minus 3 is 5, so then we'd have 5 squared, plus 2 minus 3 is negative 1 squared, and that's going to equal, well, 5 squared is 25, and negative 1 squared is 1, so we got 25 plus 1, or the square root of 26. All right, now let's look at CD. We're hoping that if it is a parallelogram, we should get the square root of 26 for the distance of that. So let's see, D is going to be our 2 coordinates, and C is going to be our 1 coordinates, and so we've got 1 minus 6 squared plus 0 minus negative 1 squared. And let's see, that's going to equal 1 minus 6 is going to be negative 5 squared plus 0 minus minus 1, well, that's going to be a positive 1 squared. And again, we can see we're shaping up to be congruent. Negative 5 squared is 25, 1 squared is 1, and so we do in fact have the square root of 26. So these two check. Now we're going to check AD, and then we'll check BC, and hopefully they're going to be congruent, and we can say that this is a parallelogram. This quadrilateral is a parallelogram. So let's look AD. All right, let's see. D will be my number 2s. So I got 1 minus 3 squared plus my y coordinates, 0 minus 3 squared. And let's see, 1 minus 3 is going to be this. We got the square root of negative 2 squared plus 0 minus 3 times negative 3 squared. And so negative 2 squared is 4, and negative 3 squared is 9. And so we're looking at the square root of 13. All right, let's see, BC. We'll do the same drill. C is going to be the 2 coordinates, B is going to be the 1, so we got 6 minus 8 squared plus negative 1 minus 2 squared. And you can probably already see this is looking pretty good for what we're wanting to do. So now we got negative 2 squared plus negative 3 squared. And negative 2 squared is 4. And negative 3 squared is 9. And we do, in fact, have the square root of 13. And so this is congruent to this. And so then we can say that, yes, this is a parallelogram since the pairs, and I could say both pairs, maybe I should say both pairs of opposite sides are congruent. All right, well, let's take a look at another one. I believe on that one we're going to use the midpoint formula. All right, so this is guided practice 4B, and I've gone ahead and graphed. Let's see what we have here. We got F Coordinates for F were -2 and 4. The coordinates for G were 4, 2. The coordinates for H are 4, -2. And the coordinates for J are -2, -1. Now you can probably look at this quadrilateral and tell that it's probably not going to be a parallelogram, but we're going to do what we want to do. And what we're going to be looking at here are the diagonals, and we want to find the midpoint of the diagonal. So we got one diagonal that is segment FH, and then we would have a second diagonal that would be GJ. So let's work on the midpoint first of FH. So we're going to do the midpoint of FH. And let's let H be our number 2s and F's be our number 1. So we got x2 plus x1 over 2. So we got 4. 4 plus -2 over 2, comma. And our y coordinates would be -2 minus 4 over, no, excuse me, these are plus. That's plus 4. Yeah, plus 4 over 2. So let's see, 4 plus -2 is going to give me just 2 over 2. And -2 plus 4, well, that's also just going to give me 2 over 2. And so the midpoint of FH is 1, 1. Now we're going to compare that to the midpoint of GJ. So let's see, GJ. And we'll let J be the number 2 coordinates, G be the number 1, just kind of going alphabetical. So then we got -2 plus 4 over 2, comma, there's our x coordinates. And then our y coordinates, -1 plus 2 over 2. Well, let's see, -2 plus 4, that's 2 over 2. Don't get too excited yet. -1 plus 2 is 1 over 2. Ah, got a difference here, because my midpoint of GH is 1, 1/2, or 0.5. And so then we would say that no, this is not a parallelogram, because the test for a parallelogram cannot be fulfilled. Now, I'm definitely going to encourage you to graph these. You can use a piece of graph paper. You can go to GeoGebra, free app. You can even graph it in OneNote, but somewhere graph these, because here's what they do, I've noticed. Sometimes these coordinates don't actually appear in alphabetical order. I mean, when you plot them, you may see them in a different order than what we see here going clockwise, F, G, H, J. There may be a little bit of mix-up up there, because you know why? Textbook manufacturers are evil people, and they love to do things to trip you up. Have fun.